Hello, and welcome to Shiksha Costa. Today we're going to be learning about zero and negative exponents. So in this lesson, we're learning about negative and zero exponents. How do you know you're good at this stuff? When you can determine through investigation and when you can describe what is the meaning of a negative exponent and what is the meaning of zero as an exponent as well. As well, on top of that, you will also be able to evaluate with and without technology, so just by hand, any numeric expressions that contain an integer exponent, which means negative exponents, and it has a rational base. So the base is like a rational number like 1.2, or the base is like a fraction, and the exponent is negative. Both of these two things are your success criteria. To get ourselves started here, let's think about this question. How can we write the expanded form of 6 to the power of 3? That's pretty easy, right? That is just 6 times 6 times 6. Well, what if we have a fraction, 6 to the power of 3 divided by 6 to the power of 2? What does the expanded form of this look like? And then can we simplify it from there? It's pretty easy to write this in expanded form as well, right? We have the top is 6 times 6 times 6, which we already know from here. And the bottom is just 6 times itself 2 times, 6 times 6. And then what would we do to simplify this? Well, we might just say, these 6's will cancel out, these 6's will cancel out, and I'm left with just 6 over 1. Nice and easy. I'm going to ask you to look at this and figure out which is the rule that we could have applied to go from here straight to here. And in fact, this is equal to 6 to the power of 1. That would be the quotient law, which says that if we're dividing two powers, if they have the same base, you could just subtract the exponents. 3 minus 2 would have got us 1, just the same way that expanding it and simplifying it got us that. Okay? So now that we are nice and warmed up, how can we use this same rule, the quotient rule, to simplify 6 to the power of 3 over 6 to the power of 5. Think about this for just 1 minute. Well, let's first use the quotient rule to actually simplify this, right? 6 to the power of 3 divided by 6 to the power of 5. Remember, you always take the numerator and subtract the denominator. We never do it the other way around. So we would end up with 6 to the power of negative 2. Now, what the heck does that mean? How can we end up multiplying a number by itself a negative number of times? In this lesson, we're gonna explore what does it mean to have a negative exponent and how do I deal with that? And to do that, I'm gonna ask you to do the same thing. I'm gonna ask you to simplify this, but instead of using the quotient rule, I'm gonna ask you to put it in its expanded form. So just take a minute, pause here, and do that. So let's try that. Let's make this its expanded form. This would be 6 times 6 times 6. That's our numerator. 6 times 6 times 6 times 6 times 6 is our denominator. And then some of these would cancel each other out, right? Just like this. And we would be left with just a multiplied by 1 in the numerator and 6 times 6 in the denominator, which I could rewrite as 6 squared. I have 1 divided by 6 squared. Now these both started with 6 to the power of 3 divided by 6 to the power of 5. So these two expressions, this one right here and this one right here, these need to be equal to each other, because they both are equal to the same thing, the same expression. We both started in the same spot. So using this idea, just taking a look at this, do you notice anything interesting? How would we go from a negative exponent to a positive exponent? See if you can come up with a rule that we could use and then test it out with two different powers. Take 2 minutes, pause here, and think about that. Hopefully you saw, as well as I did, that to go from here to here, it looks like 6 to the power of 2 just sort of went into the denominator, and the exponent just changed from being negative to positive. So to make a negative exponent positive, all we have to do is take the power and move it from the numerator, because this, remember, this is 6 to the power of negative 2 over 1. Move it from the numerator into the denominator to make it positive. And you could also go backwards. If you have a power with a negative exponent in the denominator, you can move it back up into the numerator. The reason that it actually becomes positive is because we can express any power of any negative exponent. We can use the quotient rule to express it as, the power with the same base being divided with different exponents, as long as the difference between these two exponents is whatever number is up here. So 3 is 2 less than 5, right? 2 less than 5. We could write it like this, and then we could turn it into its expanded form and cancel stuff out. And remember, because we've always left 2 more on the bottom, we will end up with 2 more over here in the denominator. So just looking at this, it's almost like if we have a negative exponent, we have to create another power, division of 2 powers that has the same base, where the exponents have a difference of whatever this number is, just so that we can expand it, cancel it out, and still end up over here. Or you could just go straight from here to here, or backwards. From then, we're going to move on to 0 exponents. And I'll ask you right now to see what you can do to fill out these 3 tables. So let's look at the first one first, okay? 2 to the power of 5, if you put this into your calculator, is 32. 2 to the power of 4 is 2 times 2 times 2 times 2, which is 16. What are the rest of these going to equal? What is 2 to the power of 3? That would be 8. And the way we got 8 is, this is 2 times 2 times 2 times 2. This is 2 times 2 times 2, right? If I wanted to go from here to here, I would just need to multiply it by 2 one more time. Right? 8 times 2 is 16. If I want to go from here to here, this is telling me, hey, you have to multiply by 2 5 times instead of 4. So 1 extra time. To go from here to here, I multiply by 2 one more time. And that means to go backwards, I do the opposite of multiplying by 2. I divide by 2. So to go from 32 to 16, I divide it by 2. To go from 16 to 8, I'll divide that by 2 as well. What would the next number here be? The way we could find out this number, of course, there are 2 ways. You could always do 2 to the power of 2, which is just 2 multiplied by itself 2 times. That's 4. Or we could just continue this pattern. 8 divided by 4. 2 to the power of 1. What does that mean? This is just 2, right? And we could get that by dividing by 2. Notice, anything to the power of 1, it's a little confusing. Hey, are we multiplying this number by itself once? Isn't that just itself? Like, yes, that's true. But some students find that a little bit confusing because, they're unclear with, like, what if we're not multiplying at all? Doesn't that mean we're not multiplying? Doesn't that break it? No, it just means that we've got that number just by itself once. And here is where it starts to get real funky. 2 multiplied by itself 0 times. What does that mean? We can't solve it like we did 8, right? We cannot say 2 times 2 times 2 is 8. What will this end up being? Your first instinct might be to say, oh, that's 0. Because if I don't multiply a number by itself at all, I'll have nothing. I'll have 0. But if you recognize that there is a pattern happening here, every time the exponent goes down by 1, we are dividing this number by 2. So if we take 2 and we continue this pattern and we divide it by 2, we won't end up with 0. 2 divided by 2 is 1. Let's see if we can extend that same idea here. So remember, this is 3 multiplied by itself 5 times. This is 3 multiplied by itself 4 times. So to go from 5 to 4 times, we can take this number, and because to get here, we multiplied by 3, to go backwards, we will just take this number and remove one of the multiplications by 3. How do we do that? We do the opposite operation, which is dividing by 3. And 243 divided by 3 would give me 81. And if you do 3 times 3 times 3 times 3, you will get 81. So to get that answer, what I would do is I would, instead of doing 3 times 3 times 3, which I could do, I'm just going to follow this pattern here. And I could say 81 divided by 3 would give me the same thing. Because 81 is 3 to the power of 4. And if I divide that by 3, I'm removing one of the 3's, right? So I'm left with only 3 3's being multiplied, and that would be 27. I could just do the, just continue this pattern. 27 divided by 3 would give me 9. And I could continue that to find out 3 to the power of 1. 9 divided by 3 would give me 3. And then if I want to find out what is 3 to the power of 0, I can just take 3, I could just continue this pattern, divided by 3, and that would give me 1. So 2 to the power of 0 is 1. 3 to the power of 0 is 1. Let's look at this with just variables here. And this is where things can get really confusing. But basically, what is the pattern? What have we been doing here? Every time we reduce the exponent by 1, so whatever this number is, n, if it was 5, to get to the next row, we reduce this number. We subtract 1 from the exponents. And then to get from here to here, we divided it by the base. We divided by 2 over here, and that was the base. And we divided by 3 over here, and that was the base. So to get from here to here is the same thing as dividing by the base, by x. And if we continue this pattern all the way down, we'll end up with, x squared. And if we divide that by x, that will reduce the exponent by 1, from 2 to 1. And if I divide that by x again, it'll reduce the exponent from 1 to 0. And what is x divided by x? Any number divided by itself? That would be 1. So what did we learn here? Hopefully you saw that by the end, 2 to the power of 0, 3 to the power of 0, and even x to the power of 0, which x can be any number, all of them are equal to 1. So when you have an exponent of 0, it is always, 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 always equal to 1. 3 to the power of 0, for example, that's equal to 1. 1 over 3 to the power of 0 is also equal to 1. N to the power of 0 is equal to 1, even if you have no idea what n is. N could be any number, and if it's taken to the exponent of 0, it's always equal to 1. 0 exponents are pretty easy to remember what they do for this reason. Anything to the power of 0, always, always equal to 1. And that's what this lesson is about. We've learned about negative or integer exponents and 0 exponents. A power that has a negative exponent and an integer as its base is equivalent to the reciprocal of that base to the opposite exponent. So here we have b to the power of negative n, where b can be any number. If the exponent is a negative number, we can actually make that exponent positive and flip the base, because this is actually b over 1, right? If any number is secretly that same number divided by 1, we could just flip it into 1 over b, and that makes the exponent positive. And 1 over b to the power of n is equal to 1 over b to the power of n itself. And the reason I know that is because I can take this n and multiply by each of the exponents here. This is 1 to the power of 1 and b to the power of 1. And 1 to the power of n will end up being 1. And b to the power of, what's 1 times n? Just n. So b to the power of negative n, any number to the power of a negative exponent, is equal to 1 over that same exact power, except the exponent is positive. And if you have the negative exponent in the denominator already, then just move it back up to the numerator. When you're simplifying algebraic expressions, and they involve exponents, it's really common practice to give your answer with only positive numbers as your exponents. And the last thing we learned here was that any power with an exponent of 0 is equal to just 1. Let's do some examples. 5 to the power of negative 2. This would just be 1 over 5 to the power of positive 2, which is the same thing as 1 over 25. What about 1 over 9 to the power of negative 3? For this, we just take the whole power from the denominator and we move it back up into the numerator and change the exponent from negative to positive. So this would just be 9 to the power of 3, which is the same thing as 729. Ooh, what about something like this? And this is about as hard as a question as you will see. And there's an easy way to do this, and there's a hard way to do this. I'm going to do it the hard way first, so I can show you all the work that you can save by remembering the rule. Okay? 7 over 8 to the power of negative 3. Well, one of the things I can do with my exponents, remember, is I can say that, this is all over 1, and I can take the entire power and move it into the denominator, and then make it positive. That would be 1 over 7 over 8 to the power of 3. Okay, can I continue to simplify this? Yes, I don't like a fraction under a fraction, like that's gross. So I'll say that this is 1 over 7 times 8 times itself 3 times. This is it in expanded form. And this is the same thing as 1 divided by 7 over 8 times 1 divided by 7 over 8 times 1 over 7 over 8. And each of these 3, I'm going to simplify this. What is 1 divided? 1 is 1 over 1 divided by 7 over 8. How do I divide fractions? What we would do is we would flip the second fraction into its reciprocal and then just multiply. Okay? So this would be 1 times 8 and 1 times 7, which is just 8 over 7. So each of these will turn into 8 over 7. And when we're multiplying fractions, just like we multiplied 1 times 8 is 8 and 1 times 7 is 7, this is going to be 8 times 8 times 8, 7 times 7 times 7. Just like this. And I'm going to express those as powers. And then notice that both of these are to the power of 3. I can use the opposite of the power of a product rule. Remember, when we have a power of a product, we multiply each of the exponents by the outside exponent. I'm going to go backwards and just say this is 8 over 7 to the power of 3. Now, this is the hard way to do it. Notice that I can express 7 over 8 to the power of negative 3 as 8 over 7 to the power of positive 3. And if I remembered that a negative exponent, all it does is it takes the base and flips it into its reciprocal. Right? I started with 7 over 8. I end up with 8 over 7. That changes the exponent from being negative to being positive. Okay? So you could go from this step to this step in just one step. You don't need to do any of this, all of this hard work that I did. And at this point, you can evaluate it, or if you're asked to just simplify, then you can leave it the way it is. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.